All right, welcome. Today we're grabbing our lab coats and putting on our detective hats. We've got a mission to unmask an unknown compound by following a trail of chemical clues. So let's get this investigation started. So picture this. You're in the lab and you get handed a vial with some mysterious liquid inside. It's a complete unknown. Your job? Figure out exactly what it is. This is the kind of puzzle chemists solve all the time, and today we're going to crack this case together, step by step.
You know, every good investigation starts the same way, by surveying the scene. Before we even think about running complicated tests, we have to gather the most obvious evidence, the stuff that's staring us right in the face. We're not jumping to conclusions, we're starting with the absolute basics.
Okay, our first couple of clues are in. We know our compound's basic recipe. It's made of just carbon, hydrogen, and oxygen. And then we get a big sensory clue. When you carefully smell it, you get this really sharp, biting odor. If you're thinking of something like vinegar, you are totally on the right track. That's our first major hint.
So, with those first observations logged, our investigation naturally moves to the next question. That sharp smell is often a dead giveaway for acidity. So we have to ask, is our mystery compound an acid?
To figure that out, we run two really simple tests. First up, the classic litmus test. If our compound is a small enough molecule, it'll dissolve in water and turn that blue litmus paper red, a sure sign of an acid. Second, we see if it dissolves in a weak base. If it does, it means a reaction happened, creating a new salt that's soluble in water. And just like that, we've confirmed our unknown is acidic. The list of suspects just got a whole lot smaller.
We've nailed down that it's an acid, but that's still pretty broad. We need to narrow the search, and that brings us to the most important test yet. This is where we find our chemical smoking gun, that one piece of evidence that points to a very specific kind of acid. This is the million-dollar question. See, not all organic acids are the same. Some are pretty weak, like phenols, but others are much, much stronger. Figuring out just how acidic our compound is, well, that's what's going to lead us straight to our prime suspect, a carboxylic acid.
And the tool for that job is the bicarbonate test. It's so simple, it's brilliant. We just take our unknown compound and add it to a solution of sodium bicarbonate. Yep, pretty much just baking soda. This test is specifically designed to only give a positive result for relatively strong acids.
And there it is, the breakthrough moment. The compound doesn't just dissolve, it fizzes. We see all these bubbles of carbon dioxide gas being released. That fizzing, that effervescence, is the undeniable sign that our compound is strong enough to react with the bicarbonate. We've got our suspect. I absolutely love this phrase from old chemistry texts. They call these compounds the carbonic acid liberators. It just perfectly captures what's happening, right? Our carboxylic acid is strong enough to force the bicarbonate to become carbonic acid, which is super unstable and immediately falls apart into water and that fizz of CO2. Most other organic acids, like phenols, just aren't strong enough to pull this off.
Okay, the fizz test points directly at a carboxylic acid, but any good detective knows you have to confirm your findings. So it's time to put our suspect in a lineup and get that final, undeniable proof. Our first confirmation test is called esterification. What we do is take our suspected acid, react it with an alcohol, and add just a tiny drop of an acid catalyst to speed things up. If our suspect really is a carboxylic acid, this reaction will create a completely new kind of compound called an ester. So, how do we know if we actually made an ester? We use our nose again. Esters are famous for having these wonderful fruity smells like bananas or pineapples, or that wintergreen scent. So if we go from that sharp vinegary smell to something sweet and fruity, that's a positive test. The case against our suspect is getting stronger. So far, we've nailed the family of the compound. We know for sure it's a carboxylic acid. But the investigation isn't over. Can we actually pinpoint the exact identity of our compound from a list of possibilities? For this, we use the ferric chloride test, which is basically a chemical police lineup. We add some ferric chloride, and depending on which specific acid we have, it'll produce a very distinct color. It's like a chemical fingerprint. Acetic acid will turn red, benzoic acid goes kind of a buff color, and something like salicylic acid gives this amazing deep violet. We just match the color, and we've got our culprit.
Now that we've identified our compound, let's talk about why all this matters. Because chemists don't just identify things for the fun of it. We use these unique properties. That strong acidity isn't just a clue, it's a tool. You could even call it a chemist's secret weapon. And this is where it gets really, really cool. That same strong acidity that made our compound fizz, it allows a chemist to easily pull it out of a messy mixture. So imagine our acid is all mixed up with a bunch of other neutral stuff. How do you separate it? Well, you exploit that unique reactivity. This procedure is so elegant. First, you add sodium bicarbonate to the whole mixture. Only the carboxylic acid reacts, and it turns into that water-soluble salt we keep talking about. All the neutral junk just sits there. Step 2, you filter everything. The solid, neutral stuff gets caught, while our acid, now dissolved as a salt, slips right through with the water. And finally, this is the magic part, you add a strong acid like HCl to that water. This reverses the first reaction, turning the salt back into the original carboxylic acid, which then usually precipitates out as a pure solid. It's an amazing purification trick. So, after a very thorough investigation, we can confidently say, case closed. Let's just do a quick recap of the key evidence that led us straight to our conclusion. This case file really lays it all out, doesn't it? Dissolving in sodium hydroxide told us it was an acid. The fizz, that effervescence with sodium carbonate, was the smoking gun that told us it was a strong carboxylic acid. The fruity smell from esterification was our confirmation, and the final color test with ferric chloride let us pick the specific culprit out of the lineup. Each test just built on the last one until the identity was undeniable.
And with that, our chemical detective story comes to an end. We followed the clues, we ran the tests, and we unmasked our unknown. But it leaves us with one final thought. We just saw how acidity can be used for separation. What other clever tricks could a chemist pull off using an acid's unique properties? Definitely something to think about. Thanks for joining the investigation.